All right, so the next chapter that we're going to cover is chapter 20 in the Klein textbook. It's all about ketones and aldehydes. We're just going to start off doing a little bit of nomenclature. I do want you to review nomenclature at home as much as possible. The nomenclature is a bit different for these, so I'll show you some examples. And we'll do a really easy one first. So a simple straight chain aldehyde. First thing you want to do anytime you're naming any organic compound is what? Longest carbon chain. And you want your longest carbon chain to contain your highest priority functional group, which in this case is an aldehyde. Do we want a number going right to left or left to right? What do you think? Right to left, right? You want your functional group to be at the lowest possible position. So I'll go ahead and number this 1, 2, 3, 4, 5, 6. So in this case, anytime you number an aldehyde, by definition, the aldehyde is going to be at carbon 1, right? All right, when we go ahead and we try to name this, what will the prefix be for the carbon chain? Hex for 6 carbons. It's not going to be a hexane because it's not a normal alkane. So instead what we're going to do is hexan-al. Al is the suffix for aldehydes. So it's nice and simple in that regard. So let's do a practice one. And this one's going to be a bit more complicated. Oops, sorry, this is an aldehyde. Forgot my hydrogen there. And in this case, the aldehyde is the highest priority functional group. So it will have an Al suffix. All right, let's try this together. Longest carbon chain, we said always starts at the aldehyde position. So we could go 1, 2, 3, 4, 5. And then we look at other functional groups coming off. We've got a bromine off of carbon 3, a methyl group off of carbon 4. And then last but not least, we also have to remember stereochemistry. So for carbon 3, is that going to be R or S? R. Okay, so now we can piece this together. And we've got to be careful to include stereochemistry first. Because there's only one stereo center, we don't have to number it. We can just say R. And then what will go first, the methyl group or the bromo group? Bromo. I want to alphabetize them. So 3 bromo, 4 methyl, and then we would go pentan al. And it's important to remember to keep this suffix, the al. Make sense? All right, let's do ketone nomenclature now. Ketone nomenclature is pretty similar, but with a few variations. And I'll again start with the really simple one. Again, we want to number our longest carbon chain containing our functional group. And we want our functional group to be at the lowest possible position. So should we number going left to right or right to left? Say 1, 2, 3, 4, 5, 6. That's better than having the ketone at carbon 4, right? Okay, so we know it's a 6 carbon chain. And in this case, we need to be more specific with the position of the ketone. Specifically, it's coming off of carbon 3, right? So what we would do is we would call this 3 hexanone. Basically, the ONE means that it's a ketone. Oop. And the 3 is the CO double bond position. Does that make sense? Yep. You normally don't see it written that way, at least for simple ketones, although I don't believe it's wrong to write it that way. So the question was, can you write hexan 3-one? I believe that is still IUPAC allowed. However, simple ketones, they just write it this way. All right. There's a bunch of special aldehydes and ketones out there, so we do want to cover some of them. And let's do the aldehydes first. First one is the most simple aldehyde, only one carbon. Does anybody know what this is called? Formaldehyde. This is what they used to use for embalming animals or bodies. It has a very distinct odor to it. However, it's been linked to many different types of cancers, so they're trying to phase it out for a lot of embalming. All right, the next one is one we've already seen. Simplest aromatic aldehyde. What's this called? Benzaldehyde. All right, then we've got another one. What would you call this using our traditional IUPAC name? Write it underneath. It's 2 carbons, so be ethan, whoops. Ethanal. You can imagine that gets pretty tricky. You have to pronounce it super clearly with an al suffix, otherwise people think you're talking about the alcohol. Because of that, people really don't like calling it ethanal because it's so easily misinterpreted. So instead of calling it ethanal, people call this acetaldehyde. And if you remember, anytime you see a methyl ketone, this is an aceto group. And so it's just an acetoaldehyde, essentially, and it's mishmashed together. Make sense? All right, there's one more. Not as common, but it's one that's shown in the Klein textbook, so I wanted to show it to you just in case. This one doesn't have a very generic name. It's just cyclohexane. Carbaldehyde. So these are kind of the 4 unique aldehydes that don't follow the normal IUPAC names. Does that make sense? All right, there's a handful of special ketones as well. First one you should know, at least I hope you do. What's this one called? Acetone. We use it to clean glassware, right? Found in nail polish remover, at least some of them. Some of them have ethyl acetate in there, but a lot of them still have acetone. The next one is one that we covered last term. What's this one called? Acetophenone. And if you remember, we've got an aceto group. So just like the previous name that we saw, anytime you see AC, you should think of a methyl ketone. The last one that we've got is pretty similar. I think some of you had this as your unknown for the NMR lab last term. Does anybody remember what it was called if you had this as your unknown? It's called benzophenone. So these are a handful of special ketones that you may run into. I will say that naming gets a lot trickier the more you know, right? So then the question is, well, what functional group takes priority? Which suffix do I use? Which one do I not use? There's actually a full IUPAC list. And this is actually from a website online called Mastering Organic Chemistry. I've got the link on the bottom. Sorry, it's actually Master Organic Chemistry. And he's got them in order of most important to least important. And you can see down at the bottom, all of these ones down here have an ANE suffix. They're all alkane derivatives, right? Those are the simple ones. And then we went through the year and we said, all right, if you've got an alkyne, it's YNE. An alkene, it's ENE, and then so on and so on. The tricky thing is, well, what if you've got other functional groups on here? If you've got more important functional groups, all of a sudden their prefixes take priority over all of the other ones. So I'll show you an example of how to use this, but I'm not going to be super nitpicky about making sure that you have this memorized. So let's do this one. Then the question is, all right, what's the highest priority here? Is it going to be the ketone or the alcohol? Ketone, right? If we look at both of them here, we've got a ketone right here. We've got an alcohol right here. The ketone's higher priority. That means we must use the ONE suffix. And the alcohol, because it's not included in the parent name, will simply be called a hydroxy group. Does that make sense? So I'll give you guys a minute to try to name this, but see if you can name it according to the IUPAC rules. All right, so let's try to number it. Where will number 1 go for our carbon numbering? At the top, right? You always want your highest priority to be number 1. Should I go clockwise or counterclockwise? Clockwise. We want to minimize numbering, so we go 2, 3, 4, 5. Then we would say, all right, this is a hydroxy group, because it's lower priority than the ketone. And what's the stereocenter going to be? S. Okay, so we can go ahead and say, all right, this is going to be S, 2-hydroxy. And then what would come next? Cyclo, pentan, one. So these do get more and more complicated the more functional groups you have, but knowing the order of IUPAC priorities can be pretty important if you've got multiple functional groups. Make sense? All right. So now what we need to do is a little bit of review, which I think preparation of aldehydes and ketones. All right. So let's start off with aldehydes, and we'll just review other ways we know of making aldehydes, and we'll start off with oxidative mechanisms for making aldehydes. And we'll try to make this a little bit quiz-like. And I'll ask you guys to help me fill in the reagent. What reagent do I need to go from a primary alcohol to a ketone? Or sorry, primary alcohol to an aldehyde? Yep. You need PCC, pyridinium chlorochromate will get you there. And if you're trying to review, this is found in, I believe, 1310 in your textbook. Oh, sorry. Holy cow. Primary alcohol, not primary aldehyde. There's no such thing as a primary aldehyde. All right. Let's do another one. Let's say I've got an alkene and I want to make 2 equivalents of this aldehyde. What reagent or reagents would I need? Yep, ozonolysis, followed by DMS or zinc and water. And if you remember all the way back to chapter 9, you can cut that double bond and insert 2 oxygens there. This was, I believe, section 9.11 in your textbook, so you can go back and review that. All right, there's another one. Or you can make an aldehyde directly from an alkyne. Does anybody remember what reagents you need for this? Give you a hint, it's 2 steps. Another hint is we've got 2 carbons here. We've got this red carbon, we've got this green carbon. Same carbons are showing up in our final product. We've got a red one right here, we've got a green one right here. Looks like we're doing anti-Markovnikov chemistry, right? It's going to the less substituted side. What reagents do we use to do anti-Markovnikov hydration for alkynes? Is 9 BBN. That was step 1, and then hydrogen peroxide and sodium hydroxide for step 2. And this was section 10.7 in your textbook. So make sure you do remember some of those older reactions. This
is the same as like R2BH.
Yeah, R2BH is sometimes shorthand for any bulky borane group. There are quite a few that are used. The key thing with this is it must be a terminal alkyne. Oh. What happens if you use an internal alkyne where you've got carbon groups on both sides? You'd make a ketone, right? So we don't want to make a ketone, we want to make an aldehyde. All right, let's do the same thing for ketones, and we'll do some review. All right, so for ketones, we can prepare them through a variety of oxidation reactions. This time we're going to use a secondary alcohol. We're going to make this into a ketone. What reagent do we need? You can use PCC, or what's the other reagent? Chromic acid. And chromic acid can be made by mixing sodium dichromate with sulfuric acid and water. This was section 13.10, I believe. Depends on the edition of the textbook that you have. Alternatively, just like before, you can take an alkene. However, this time, we don't have any hydrogens coming off the alkene. It's tetrasubstituted. Same reaction. Do O3 and DMS, dimethyl sulfide, and you can get two equivalents of a ketone. And this was section 9.11 in your textbook. So just like with aldehydes, but we have to be careful with our starting alkene. All right, then going back further, we can make a ketone this way, where we've got a carbonyl, this time coming off of the more substituted carbon rather than the less substituted carbon. So let me actually change this to a green C, just so we're color coding appropriately. How do we do that? You need acid and water, so H2SO4 and water. And then what was our catalyst? Does anybody remember? Yeah, mercury 2 sulfate. Usually any mercury 2 salt will work though. All right. There's also one more we saw recently. And what reaction allows this transformation? Anybody remember the name of it? Starts with an F. Friedel-Crafts. Right? And that was where we had our acid halide. And then what was our catalyst? Yep, aluminum trichloride. So we covered this. Well, I can't remember the section in it. It was last chapter, though. And this one was section 10.7. So make sure you do review those if you are rusty at all. Make sense? All right. Aldehydes and ketones can be quite reactive, which is why they're really useful intermediates in organic chemistry. So let's take a look at why they're so super reactive, and then try to predict which one's more reactive. And we'll start out with just a simple aldehyde. If you think about a simple aldehyde, it's got a resonance structure where you can kick up electrons onto the oxygen. And it's got a partial positive charge, right? If you think about ketones, ketones can do the same thing. where you can kick up those electrons. And have a resonance contributor on the right. So same exact electron pushing. All right, and if we look at this, right, that means that this carbon or this carbon are susceptible to attack, right? Are they electrophilic or nucleophilic carbons then? Not everybody all at once. Electrophilic, right? Positive carbons want electrons. So these are electrophilic. All right, now the question is, which site is going to be more reactive than the other and why? So I'll give you guys a minute to talk about this with your neighbor, but see if you agree. All right, raise your hand if you think aldehydes are more electrophilic. That's good. Why are aldehydes more electrophilic? They're less stable. Why is that? Yeah, they only have one R group. If we think about carbocations, right? We said carbocations are more stable the more substituents you have coming off of them, right? So tertiary is more stable than secondary and so on. In this case, you can tell it's less stable because it doesn't have as many carbon groups off of it. So it's less substituted equals less stable which means it's more reactive. Does that make sense? All right. So in general, aldehydes are going to outcompete ketones. If there's a nucleophile around, the nucleophile will prefer to attack the aldehyde before it gets a chance to attack the ketone. So let's look at some basic mechanisms where nucleophiles attack these electrophiles. And this one's going to be under basic conditions. All right, so let's do an aldehyde. We know these are really reactive. And we're just going to make up a nucleophile. Because it's under basic conditions, there's a fair chance this nucleophile is going to have a negative charge. It's pretty intuitive. This is going to attack the electrophile, and then we're going to kick up electrons onto this oxygen. However, this is under equilibrium conditions. Actually, I'm going to swap this around. I'll do oxygen on this side, hydrogen here, and then the nucleophile here. And then last but not least, there's usually a proton transfer. Where this oxygen can then attack the proton. And you end up with your final product. If you notice, though, we did end up making a stereocenter, so you end up with a racemic mix. All right, so now the question is, well, can this go backwards and do the opposite reaction? What do you guys think? Be like, yeah, you drew equilibrium arrows. Of course it can, right? So why might it favor the right-hand side over the left-hand side? Potentially temperature can change things. Also, stability of your nucleophile, right? If you've got a really, really unstable nucleophile, that will favor formation of the products. What's another thing we could do that you might remember from Gen Chem? Give you a hint. Think of Le Chatelier's principle. You guys remember that? Anyone? Bueller? You can flood the reaction with your nucleophile, right? So if you flood the reaction with your nucleophile, it's going to push the reaction more towards the right-hand side. So quite often this is run with an excess of nucleophile if you're trying to get the product on the right-hand side. All right, let's do the same mechanism, but under acidic conditions. All right, so just like before, we're going to have an aldehyde. But the fastest reaction in chemistry is always going to be our acid-base chemistry. So if we do have an acid source around, we're immediately going to protonate that carbonyl before anything else has a chance to occur. And this is assuming we have a pretty strong acid. I think the pKa of a protonated carbonyl is about -7. So you have to have a very strong acid to protonate a carbonyl. All right, and then if we have a nucleophile around, that's just going to be hanging out. And quite often, this nucleophile has a proton on it because it's under acidic conditions. It doesn't like to have a negative charge. This will attack, kick up electrons. However, your nucleophile now has a positive charge, so what do you think the last step will be? Deprotonation. So I'll just write -H plus, and clean up these arrows. And you can end up with a similar product. So it's a pretty similar reaction to the top one. You're just changing your proton transfer from the last step to your first step, right? The big thing is always remember that under acidic conditions, that means you want to avoid negative charges. You see how in the acidic condition mechanism, I only ever had positively charged intermediates? That's important. And under basic conditions, you want to avoid positive charges, right? The only exception to this is obviously your conjugate acid or conjugate base. Does that make sense? Okay. There are some notes that I want to keep track of for both of these reactions. One is it is equilibrium conditions. Meaning it's not a one-way arrow, it can actually go back and forth. Product is favored with unstable nucleophile, or if nucleophile concentration is high. Sometimes it's a combo of one or the other. If your nucleophile is also a good leaving group, then products are favored. Or sorry, then starting materials are favored. And then, like I said before, aldehydes tend to be more reactive and are more susceptible to these reactions than ketones. More likely to form the addition product. Does that make sense? It's really easy to forget that these are under equilibrium conditions, and you have to be very careful with it. Equilibrium conditions are a double-edged sword. Sometimes people will say, well, what if you're only getting 1% of your product? Sometimes that doesn't matter. That 1% is enough to carry on to your next step. However, you do need to be aware of your nucleophile concentration, whether or not it's run under acidic or basic conditions, and in some cases what the pH is, and we'll talk more about that later. So let's look at some commonly used nucleophiles for these addition reactions. All right. And there's quite a few. However, the reactions are very similar, the mechanisms at least. So let's do oxygen-based nucleophiles. The simplest one is going to be water. When these attack into ketones or aldehydes, they call them hydrates. Alternatively, if you're going to run this under basic conditions, you can run this just with sodium hydroxide or potassium hydroxide. You can also use alcohols besides water, and we'll talk more about that later, and that's what you see in your pod, is you've got an alcohol. And then you can also do a reaction with diols, and we'll cover these reactions later. It's kind of a neat trick that you can do with diols. You can also do sulfur nucleophiles. You can use hydrogen sulfide, although I don't think most people do because that's incredibly stinky and it's a volatile gas. However, you do see the mercapto version. So you've got two sulfur groups on there that's similar to the diol on the bottom. You can also use nitrogen nucleophiles. These are quite common. You can use primary amines. You can use secondary amines, but that's usually about it. Whoops, sorry, that should just be R2NH. You can also have hydrogen-based nucleophiles, which we've actually seen already. So what if you want to add in a hydride? What reagents can we use? Whoop, that's not a hydrogen. So let's say we go back up and we look at our mechanism. What if we want this nucleophile to be a hydrogen? How can we do that? So start out with an aldehyde and go to an alcohol. A Grignard would add in a carbon. We'll get there next. But what if we want to have the nucleophile be a hydrogen? NaBH4, sodium borohydride. You're close with the NaH. The problem with NaH, if you remember all the way back to first term, is it's insoluble. It only does surface acid-base chemistry. It's not as readily available to act as a hydride nucleophile. Alternatively, what's the other one that's the stronger hydride source? LAH, or LiAlH4. Whoops. Both of these are good hydrogen nucleophiles. All right, then the last one is carbon nucleophiles. Somebody already said it, but if you've got a Grignard reagent, right? That Grignard reagent we know can attack into aldehydes and ketones. This is always going to be under the basic condition mechanism. You can also have cyanide act as a nucleophile, although most people avoid it because it's somewhat toxic and dangerous to run. And then the last one that's kind of neat that we're actually going to cover later is this goofy looking reagent where the carbon has a negative charge. Got three phenyl groups coming off a phosphorus, and then the phosphorus has a positive charge. This is called the phosphorus ylide, and we'll go over this in more detail later, but this is used in the Wittig reaction. All right, so we've got quite a few reactions that all use almost the exact same mechanism with the exception of the Wittig reaction, that one on the far right-hand side. Does that make sense? All right. So let's just start with oxygen nucleophiles and then kind of work our way to the right slowly over the course of the week. So let's do oxygen first. Let me change this for 1 second. All right. So with oxygen nucleophiles, you can actually do something that's kind of unique. Actually, sorry, I'm going to change this to an R group. You can add in an alcohol, right? Just like we saw in the other mechanism. This is referred to as a hydrate. This can occur under acidic or basic conditions like we saw in the previous example. I will show you something kind of funny with this though. If you take acetone and water, you can have an equilibrium reaction where you form the hydrate of acetone. That's possible, right? And then we could also have a similar reaction with formaldehyde. Where you form the hydrate. Which one's more likely to be on the right-hand side, the top equation or the bottom one? So which one's more likely to form product? The acetone reaction or the formaldehyde reaction? Why? Yep. Why formaldehyde? Because it's an aldehyde, right? We just finished saying aldehydes are more reactive. And this is actually proven in labs. Formaldehyde is actually very, very hard to isolate. Usually it's sold as a hydrate, and that's what they use, or they sell it as paraformaldehyde. So that's present at about 99.9%, where the ketone, on the other hand, only gives you about 0.1%. That's a good example of showing how much more reactive aldehydes are than ketones. Aldehydes are very susceptible to hydrate formation. Ketones, for the most part, aren't. All right. So really briefly, let's do another practice mechanism just so we drill it into our heads. Yep. Yeah, just 1 second here. Yep. All right, so let's do the acidic mechanism for hydrate formation. And we'll stick with formaldehyde because we know it's super duper reactive. What do you think the first step's going to be in the acidic condition mechanism? Protonation, absolutely. Fastest reaction in chemistry is protonation. Or sorry, acid-base chemistry, I should say. So we'll protonate our carbonyl. And then in the next step, we have water floating around. Water, we know, can act as a nucleophile, attack in, kick up electrons onto that oxygen. So one of these lone pairs. Water, when it attacks in, still has a formal positive charge, right? Which is good because we know under acidic conditions we want to avoid negative charges. And then in the next step, typically we're trying to drive the reaction to completion, so we have excess water around. So water can deprotonate, or you can just write minus H plus. To get to your final hydrate. The main thing to remember, though, is if we look at this, we're putting acid in and we're pulling it out. What does that mean regarding the acid? It's catalytic. So we're regenerating it at the end of the reaction. All right, the basic mechanism is also pretty similar, but I want to practice it. Again, we'll stick with using formaldehyde. Actually, I'm going to show it a little bit differently. Oops. Why am I struggling with this? You can use a stronger base and deprotonate water to get this to work. Most people, it's just easier to use sodium hydroxide in water, but I'll show it this way just to be somewhat consistent with our previous mechanism. And in the next step, this can attack in, kick up electrons. Oh, should be an oxygen with the negative charge. And then your conjugate acid can donate the proton back. And you can end up with your hydrate. Let me flip this around just so it looks better. Just like before though, we can see our base is being regenerated. So again, the base is catalytic. Does that make sense? It does depend though, like I said, usually this reaction is just done with sodium hydroxide or potassium hydroxide, so you don't have to worry about it being catalytic. You're just shoving in a bunch of hydroxide to favor formation of your product. All right, there are some strange examples though. Strange ketones can form hydrates. Normally they don't like to, but let's take a look at an example here. So under catalytic acid conditions, sorry, this should still have fluorines on it. You can easily form a hydrate with this molecule. And when you do this, this shows up about 99.9% versus our normal acetone. If you remember back from the previous slide, I said this is only formed in about 0.01%. Tiny, tiny amount. Why is that? Yeah, what do we call that when we've got electron withdrawing groups? Not immediately attached, but attached further away. Anybody remember the term? Induction, absolutely. Yeah, if you remember, induction is where you've got electron withdrawing groups kind of sucking electron density out of there. That means that this carbon is very electrophilic. Due to induction. So there may be some situations where you have ketones that are inductively withdrawn or have other unique properties that make them more susceptible to attack by a nucleophile. All right, I think that's where we're going to stop today. Tomorrow we're gonna jump back in and we'll do the same sort of reactions with alcohols. So we'll stop there today.